Okay, all right, I'm going to leave this here like this. What's that? Am I scared to come? Oh, is everyone? Yeah, well, maybe. I had some people ask me. I'm sorry. Did I hit record? Yeah. I didn't update you all about what happened the other day because I don't have any updates. I called the campus police and they said, yeah, we're aware of the incident. And then they told me like everything is like normal. So whatever that means. And then I heard some other stuff, like just, you know, secondhand stuff, so I don't know if it's valid or not valid. They told me that whoever it was a student in a class and that they were arrested, but I don't know if that's true. So
MJ works in the gym in this class, put in the class group chat that he was escorted off campus by police and that we wouldn't be seeing him again, at least not in the gym.
Okay, yeah.
I mean, it was a mess. Right, like you're going to die out of school and start having these school
Yeah.
shootings.
Yep. All right. So, but given this situation, we're going to pull the little magnetic thing out of the door just to have it. And do y'all remember the first day of class? Didn't we talk about that's an exit point? Did we talk about that day one? We did. We didn't. That was Cal 2. Okay. This is an exit point. This drops off to a little, it's like a little awning right here. I mean, it's literally right there. So that is a way out, just so we know. Okay. I mean, you still would have to jump down somewhere, you know, but
I think I'm heavy enough to just throw myself through it.
we'll throw you through it. How about that?
Like 3 students.
And multiple oceans from the movies.
All right, let's get going here. So mini exam 7, right, is here. Now, there's a little discrepancy on that mini exam 7. It was brought to my attention that in the email I said it was due on Thursday, and then on the exam I said it was due on Thursday. But verbally in class I said it's due on Wednesday. So I'm going to honor what was on there. If you want, you can have your exam back, but you have to email it to me tomorrow by 1 p.m. If you're happy with what you have, turn it in, that's fine. So, anybody want to revisit anything on theirs? Okay. We're keeping that locked. Yeah, pull that thing out. Thank you. Anybody else? So you have to email it to me tomorrow by 1 p.m. And when you email it, there's a catch. Has to be a single file. Don't send me an email with 10 pictures. Somehow you have to condense it down to a single file. PDF would be preferred. I think 2023, most of us can do that now. Yeah? Okay. All right. We good? Let's get to an example. I was thinking of just continuing to plow through here, but then I was like, you know what I'm gonna do? I'm gonna go pick a problem out of a book. I just grabbed a calculus book off my bookshelf, took a picture of a problem, and we're just going to do this. So what we want to do here is calculate. Let me put it up here first, and then we will All right, there we go. Is that someone coming in? No? Yeah. You don't mind, let them in.
Is it really secure if we just let everybody in?
let everybody in. Yeah. Yeah, don't look at who it is, just let them in.
Took the last one day.
Yeah. Yeah, you know, the data shows that most of the time
They're in the class.
they won't breach a door. They'll just go to the next open door, but whatever. All right.
I just love that we have to think about that.
Yeah, hey, yeah, this is the world we live in, right? All right, y'all ready? Let's do it. So we're asked to find the line integral, right, over the closed curve, right? It's closed, you can tell because this notation, right? Closed curve, positive orientation, that means we want to go counterclockwise through this curve. Over the vector field, right? Or this vector field where I give you the vector field, all right? So let's draw this curve first, C. I'm going to draw it over here. It's the box bounded by the lines x equals plus or minus 1, y equals plus or minus 1. So you've got two vertical lines, two horizontal lines, y equals plus or minus 1. Yeah, you see it? Everyone see it? So it's this curve right here, C, goes like this, like this, like this, like this, and we're going positive orientation. So we're going counterclockwise through there. All right. Now, what was do y'all remember what the end of class was last time?
Scared.
Scared. Green's theorem, okay? So let's go back and look at what Green's theorem said. Green's theorem says that, right here, if we're trying to do the line integral over the closed curve positively oriented, how do I know that's positive oriented, not negative? The circle doesn't have an arrow on it, right? If I had the arrow going clockwise, like a little arrow like this, then that would tell you it's negative orientation. So without the arrow, it meant it's clockwise, counterclockwise. So if we're trying to do a line integral of over C of p dx plus q dy, that we can turn this into the double integral over d of the partial of q with respect to x minus partial of p with respect to y, all of that with respect to area. Here, p and q are the, well, they're scalar functions, right? And d, what is d? Yes, but how is it related to c? So the C is a closed curve, right? D is the region that it encloses, right? So instead of doing the line integral over the curve, we can do the double integral over the region D. That's what Green's theorem says. Now, for us, we have f dot dr, right? So can we use Green's theorem? Well, we have to realize that what this is, what this really means, right, is this is the line integral over C of, let's call this right here, let's call this P, let's call this Q. This is P dx plus Q dy. Now, how do we know that? I showed you that at the very beginning of class last time, right? Do you want to see it again? I'll show it again. It was at the end of 13. Come on. Where the heck is it? It's coming. There we go. Okay, right there. So this is note 13.2.19, right there. That this breaks up into this. Now, if your vector field is two-dimensional, then of course you wouldn't have this piece, which is what we have here, right? We good? All right, so I'm about to use that. I'm about to use that because this, by Green's theorem, right? By Green's theorem here, is going to be the double integral over d of the partial of q with respect to x minus the partial of p with respect to y dA. So what we're saying here is instead of having to go around this thing, right, which would require we find the parametric representation of 4 different line segments, C1, C2, C3, C4. Instead of doing any of that, all we have to do is find the double integral over that region D of the difference of those partials, all right? So this is our D here. All right, so how about we do some partials, yeah? Let's figure out what is the partial with, you know what, I think I can probably just go right to this. Let's continue from this. This is going to be the double integral over the region D. What is the partial of Q with respect to X for us? 0, right? Yes? And then minus 0. Which would be? I forgot to put dA here. Which would be 0. Do you think that's a little bit nicer than, yeah? Nicer than actually going and trying to do that by hand?
It was a little quicker.
Yeah? Okay. Now, most of them won't turn out to be, 0, but it just, again, goes to illustrate the idea that we can go from a ugly thing that requires parametrization to something that would be hopefully better, all right? All right, I think I want to continue with the Green's theorem. We're not done with it. There's something else in here that is quite interesting. I cannot see it. My eyes have gotten so bad. So we ended class with that example right there. Remember that example? It looked really bad, and then we said, hey, let's do Green's theorem, and it turned out to be really easy, right? So we see that when we have line integrals, sometimes we can convert them to double integrals, right? That's what Green's theorem tells us. We can go from a line integral to a double integral. But in certain scenarios, you can actually go from a double integral to a line integral. So how would that work? Remember from a couple of sections ago that if you're doing the double integral over D of 1 dA, that gives you the area of the region, right? That formula right there. So if you've got some region D and you want to find its area, the area of that is the double integral over D of 1 dA, right? We know that this is something we've already established. So if you look at Green's theorem had that double integral, and there was partial Q with respect to X minus partial P with respect to Y, right? That was Green's theorem. In what scenarios would this argument in here, this integrand, when would it be 1? Because if this is ever 1, then aren't we just finding the area of something, right? There's a couple of different scenarios where this could be 1, right? There's a couple of different scenarios. How about this scenario right here? What if I come in here and I define the P function to be 0 and the Q function to be X? Then do you all agree that that would give you a 1? Yes? And that means that this right here, right, the area, that integral right there has a 1 in it now. That area is just converting back to the line integral is this. Why is it this? Can somebody tell me why it's that? Let me put Green's right here. Green says this is P dx plus Q dy, right? The line integral over closed C. So if this turns out to be 1, using this for Q and this for P, do y'all see if P is 0, right? If P is 0 and Q is X, then that is this, isn't it? So this line integral represents the area of the region D. You're going to have to see an example play out, all right? But does that kind of make sense? Is that the only way we could have got a 1 here? Now, we probably could have made different choices, right? So let me show you another option. I'm going to leave that right here because I want to reference that again. How about this option 2? Let me get this one out of the way. Look at this scenario right there. What if I come in and I say, all right, well, another way I could get a 1 here is if I let my p function be negative y and let my q function be 0. And now when you do these partials, you would get, what's this one? That would be 0. Then minus, this one would be negative 1, right? Partial of p with respect to y would be negative 1. That goes right there. Partial of q with respect to x is 0. So you get 0 minus negative 1, which is positive 1. And then given this p and this q, plug into here, and you just get negative y dx. Y'all see how this is working? It's just picking, like choosing a clever choice for the p and the q functions. Last one. By the way, there's an infinite number of ways you could do this. This is just a couple of examples. Another way I could get a 1 there is I could let the p be negative 1/2 y and the q be 1/2 x. Let's check. What's the derivative of q with respect to x? So what's the derivative of that with respect to x? 1/2. And then subtract from that the derivative of that with respect to y. Negative 1/2. So you have 1/2 minus negative 1/2, which is 1/2 plus 1/2, which is 1. Right? And then again, you replace the p here with that function, you replace the q here with that function, you get this. Those are 3 different ways that we could look at a double integral, the area of a region, as a line integral. Let me say it again. This is 3 different ways that we can look at the area of a region as a line integral as opposed to a double integral. Y'all look tired. Okay, so green, yes.
So only if the partials of p and q add up to 1.
That's right.
Look at it as a line.
That's right. So generally the Green's theorem is to make line integrals easier, because you take the line integral over a closed curve and you say, hey, I wonder if I can do this as a double integral over the region it encloses. If we look at just want to know about the area of a region, we can actually convert that to a line integral, and sometimes it's easier to do that. Let me do this example, which I think you'll find somewhat, I'm not going to say beautiful, but it's pretty amazing if you ask me. We're going to prove that the area of a circle is pi r squared. And we're going to use it we're going to do it using Green's theorem. Okay, so let's think about how we do this. The area, we have a circle of radius r, right? Can you come up with a double integral for that? What would it be? It's the double integral over that region D, right? Let's say region is this region in here, right? Call that D of 1 dA, isn't it? I mean, that's the definition of the area of that region. Yes? But I can turn this into a line integral over the closed curve C. And I showed you 3 different examples of how I could do it, right? 3 different ways. And the one I think I'd like to choose, which one? Let's choose the first one. On the first one, what we did is we defined the p function to be 0 and the q function to be x, right? And when we do that, then the area becomes this line integral, right? So if we let p be 0 and q be x, then that area becomes this line integral. So using that, we need to actually talk about what C is. So C is this curve, right, that goes around. Can you give me a way to find, or give me a parametric representation of that curve? C goes around, right? Yeah, so C is just What is it? Careful.
R cosine.
Yeah, so the x of t is r cosine t, right? And the y of t is r sine t. And t here would have to be bounded between 0 and 2 pi, right? That draws me the curve C. And so what I'm going to do here is this line integral right here, right? X dy, which for us is the line integral. Okay, so now C, we're going to replace it with our restrictions, 0 to 2 pi. And then what's x for us? R cosine t. So r cosine t times, all right, what's dy for us? Well, here's y, right? Derivative of that is r cosine t dt. Yay or nay? So, looks of confusion, no? No? So now what? Yeah, how are you going to do this? It's cosine squared, right? Integral. So you're going to have a half angle. So let me go, keep going. How about the r times r? Pull out, right? It's a constant, right? So r squared comes out. Ooh, pi r squared. 2 pi. This is cosine squared t dt. And now I'm gonna do this whole integral, and it's not that bad. So let's just finish it up. But before I do that, I mean, does anyone have any questions? I mean, I'm trying to get you to see like the actual power of this. If you this is saying that if you want to find the area of any region, as long as you can come up with the parametric representation of the curve that goes around the region, then you can actually evaluate the area using a line integral. Isn't that weird? That you can find the area of this by somehow just going around it. Strange, right? Strange. All right, continuing. So this becomes, that I'm going to power reduce, so I'm going to have a what? 1/2 times the quantity 1 plus cosine 2t. So the 1/2 is going to come outside. R squared integral 0 to 2 pi. That turns into 1 plus cosine 2t dt. What is that identity called? The one that takes you from there to there? It's called different things by different books and different authors. I call it the power reducing formula because it reduces the power, like gets the power from squared down to not squared. But either way, you should all be familiar with that from Cal 2. Half angle, right, is another way. Let's get the antiderivative. Antiderivative of this is just t, right, t, and then here we have to scale, right? We have to put a 1/2 out front, sine 2t. And now we're going to evaluate that from 0 to 2 pi. Almost done. Evaluate now. So what happens when I plug in 2 pi? Let's do these two things separately here. When I plug in 2 pi, I get 1/2 r squared. Then I have 2 pi goes in for t, right? And then 2 pi goes here. 2 times 2 pi is 4 pi. What's sine of 4 pi? 0. So that kills that off. So this is going to be plus nothing. And then over here, we're going to plug 0 in. 0 in for t here, 0. Sine of 0, 0. That all goes away, right? So what are you left with? I have too many parentheses. Well, I should have had a 1/2 r squared here. This is all gone, right? So what am I left with? Pi r squared. All right, we just proved the area of a circle. Yes?
Can you use this method to like find the area and extend it up and find the volume?
Well, are you talking about something where above it is uniform, like a flat plane, or like it's?
Either one.
Well,
No, for the flat plane, you can just multiply it.
yeah, just multiply by a number. So doing it, extending it further up, we're going to have a version of Green's theorem in 3-dimensional space. Okay, that's like the ultimate goal of this chapter, or this chapter is that we're going to do something like this for instead of an area like a region, we're going to have a volume. And so instead of trying to somehow figure out the volume looking at the inside, we're going to do something around the outside. And that's called the divergence theorem. So we're getting there. We're getting there. All right. That was just to show you pi r squared, right? Area of a circle. How about this one? Now that's not something that you see every day, right? I have provided for you the parametric equations, x equals 5 cosine t minus cosine 5t, and then y equals 5 sine t minus sine 5t, 5 sine t minus sine 5t, for t goes between 0 and 2 pi. If you were to plot that, graph it, using your parametric mode on your calculator, you would get this epicycloid, is what we're calling this, all right? Cool shape, right? What's the area of that? What's the area of that, right? I mean, like, how would you ever figure out the area of that? That seems very, very difficult. No? Yeah?
You find the area of one clover and then you divide.
Okay, you could do the area of one, right? You could do area of one of them, and then you could multiply by 4. But how are you going to find the area of this? Like, even if you do one quadrant, right? How are you going to find the area of that? It's not a polar region. It's not a type 1. It's not a type 2. It's, right? It's weird. I mean, look at these are the parametric equations, right? Yeah. Green's theorem. Okay, watch. We want the area of this, right? The area of this is just the double integral over d of 1 dA, right? If this is d, we want to find that area, right? Green's theorem says that, hey, great. Well, if you know the curve that draws the region, then you can evaluate the area. I just said that's crazy. Do you agree? That's kind of crazy. If you just know the curve that draws the region, you should be able to find the area of that region using this Green's theorem. This becomes the line integral over the closed curve C of, remember there were 3 different ones I could use, right? Which one did we use last time? It was xdy. We could do, what's the other one? It's negative y dx, or there's one with halves in it. Which one you use is really up to you. Sometimes one is better than the other. I'm just going to stick with x dy because there's no negatives involved. I'm just going to hope for the best. Feel free on your own when you're sitting around this weekend bored to do negative y dx. You'll do it. All right. So what do we need in order to use this? We need the parametric representation of the curve, which was given to us. See? I mean, like, we don't even have to work for it. It's there. And then we need dy, so we need the derivative of the y component, or the y function, right? Do we have the limits on t, the limits that we'll use here? Yeah, they're given, 0 to 2 pi. I mean, this is like just set up for us. Do you see that? Let me see if we can plug everything in. We're going to go integral from 0 to 2 pi. Okay, what is x for us? It's not pretty, but it's there, right? 5 cosine t minus cosine of 5t. That's x, right? That's x. And then the next piece is dy, which is the derivative of the y function. All right, let's take that derivative. The derivative there would be 5 cosine t minus, careful, you're differentiating, not integrating. 5 cosine 5t, right? Right? So we're differentiating this one, and we just get this. Does this bother you? I was watching someone do a video the other day with this, and it annoyed me that they were using a stick. I was like, that's really annoying. And then I do it every day. The lasers don't come out on camera, right? So when I'm like pointing, and you can't see it on camera. So you never noticed? You won't not notice now.
Yeah.
So, all right, now how does that integral look to you? Little multiplication, right? I mean, it's going to be not terribly pretty, but is it doable? I mean, that's really the question. Is it doable? Well, it's doable by Wolfram, that's for sure, right? But is it doable by us? All right, so your calculator, right? So let's just expand it out real quick. What would our first term be here? 25 cosine squared t. And then when we do this one, is that the same as the middle term or no? They're not the same? Are they same? Yeah, they're the same, aren't they? This and this. I'll go one at a time. So we get minus 25 cosine t times cosine 5t. And then in the middle, I have the same exact thing. Why did I say minus 20? Oh, they're not. So minus 5. And then cosine 5t times cosine t. I'm going to put them in this order. Is that right? You all happy with that? Last multiplication, here to here. Plus 5 cosine squared 5t, all of this dt, right? Let me go one more. We can put those middle ones together, right? These two are the same. So let me go one more. So integral 0 to 2 pi, 25 cosine squared t minus 30 cosine t cosine 5t, and then plus 5 cosine squared 5t dt. Let's just talk about these. What do you think about that? Could you do that? Power reduce, right? You could do it.
Take me a couple of tears.
Let's forget this for a second. How about this one? Yeah, you can't put these two together, right? Because they have different arguments. But you could do power reducing on both of those. This one, back in pre-cal, we have a product to sum formula. There's some trig that we could do to get this to work, right? In other words, it's doable. And I'm not going to do it. The whole point of this problem is to illustrate to you that getting that area initially seems pretty hard, but once you have Green's theorem, as soon as you get it to the integral, we can just use the technology to get the answer, which is what I did here. I just went in and put this in my computer, and it got me an answer. The answer is 30 pi. Yes?
Do you know what the trig identity is called that lets you, or the sum whatever you
Product to sum.
Product to sum.
Product to sum. There's other things that we could do on it, but that's probably the cleanest. Let me see here.